Okay, everyone, good morning, welcome back. A few announcements. I think on Wednesday, tomorrow is Wednesday? Time. Anyway, there was going to change the schedule, and Wednesday afternoon is now free. Is that correct? Okay. Okay, and also you have hopefully all registered for the dinner. That will happen on Thursday at 7 p.m. Those of you who registered will get an email about that. Okay, and that's, I think, all we have announcements-wise. Now we're very happy to have Zohar telling us about renormalization group flows on line defects and one-form symmetry.
Thank you so much. Yeah, thanks for organizing this fantastic event. Do you guys write here from right to left or left to right? Okay, so it's I'm gonna stick to the convention that D will be the number of space dimensions, and I'll also make an assumption throughout the talk that there is some conformal field theory at zero temperature. So it's in the language of condensed matter. I'll assume that we're at the second order phase transition at zero temperature. And, well, in the language of high energy physics, we have a conformal field theory. And I'm just trying to introduce what is the question. So that is the setup. Of course, this setup is something that people have been considering various aspects of this setup for ages. Just wait a second. So let me try to explain what is the problem that we're thinking about. First, I'll say that everything I'm going to say today is based on several papers with Gabriel, who is in the audience, Cuomo, Avia, Raviv Moshe. There are several papers that I'm going to talk about today. Mark Mezeyer, these people were involved in various subsets of these papers. And also, at the very end, I'll talk about work in progress or work to appear, depends whom you ask, where also Ofer Al-Haroni is going to be a co-author. And of course, there are many other relevant references, some of which I'll mention, and many people in the audience contributed to this subject. I'll try to do some justice to the referencing, even though partial justice. So the setup is, again, these space dimensions with zero temperature conformal field theory, D+1 space-time dimensions. And most of the work on this subject in several decades has been on understanding local operators, which are labeled by some crazy index. There are many, many local operators. And, people concentrate mostly on primary operators. There are nice highest weight representations of the conformal group. And a lot is known about correlation functions. We know some things about the density of operators. We had a very nice talk yesterday by Julian about aspects of chaos and correlation. There's lots of stuff that people have studied about local operators. However, if you ask, what about line operators? So these are operators which are not localized at a space-time point, but localized on a line in space-time. This is the line in space-time. Very, very, very little is known. So today my goal is to tell you some new things about line operators in the Wilson-Fisher fixed points and also in some very simple gauge theories. In both cases, the story is far from completely understood. So, what is a conformal line operator? Let me just define that. It's analogous to a primary local operator. So a conformal line operator is any line operator which, if it's straight in space-time, let's say it's directed towards time, so that we have a nice condensed matter-like interpretation, which I'll talk about in a second. So this would preserve an SL2R subgroup of the conformal group, which is SO d plus 1 comma 2. Okay. So if you have a line operator, and in the presence of this line operator, there is SL to R symmetry, then you say that this is a conformal line operator. It doesn't mean that it's non-trivial yet, like local operators could be the unit operator, but this is what we mean by conformal line operator. A conformal line operator is any line which, if you put it like straight up running in time, then correlation functions of local operators in the presence of this line obey SL2R worded entities. That's the definition. Similar to the question of what is the space of local operators, what are their scaling dimensions, in this setup we ask what is the space of line operators and what are scaling dimensions. What do we mean by scaling dimension? There are operators that are localized on the line, and there are operators that are outside of the line. Their scaling dimensions are like basically the bulk scaling dimensions. But operators that sit on the line, they have eigenvalues under this SL2R, which I'll call delta defect, okay? These are scaling dimensions of defect operators. There are eigenvalues of the Cartan of SL2R. Their physical meaning is scaling dimensions of operators localized on the line. And so you would like to find those scaling dimensions. And there's of course much more data. There's more data. You could also have two defect operators. You could study their OPE. You could try to expand bulk operators in terms of defect operators. There's lots of structure, which is in principle observable.
Am I allowed to take defect operators off the line, or are they stuck there?
Defect operators are, by definition, on the line, and we ask what are their scaling dimensions. In some special cases, let's say this line is okay, let me do a very trivial example that will be important. The trivial example is when the line operator is the unit operator, completely empty. This is the unit operator trivial. This is the trivial line defect. In this case, the scaling dimensions of defect operators are the same as the bulk scaling dimensions, because if you take an operator, you can always bring it to the line because there is just nothing there, and obviously, bulk scaling dimensions and defect scaling dimensions are all the same, and the spectrum of operators is the same. In the general case, however, there are many operators that cannot be brought out of the line. They're stuck to the line. Some operators can be brought out of the line, but then their scaling dimension changes. So in general, there are operators here that don't exist in the bulk. So the spectrum of operators on the line and their scaling dimensions in general has nothing to do with the spectrum of operators and scaling dimensions in the bulk.
Can I ask a question about the analogy to the primary operators?
Yes.
You said for local operators, we know that we have a lot of operators. Some of them are primary, and we get the rest by acting on those with nice things that we understand. Is the same true for line operators, that we have some that preserve this, and we can get all the rest by?
Yeah, probably you can. Probably you should think about line operators that are not straight, but they're obtained by acting with special conformal transformations, okay. So they'll have a slightly different shape.
Okay, and do you think that gives all of them? Or?
No, this just gives a tiny...
okay.
Yeah.
Okay, so it's just much bigger than the space of...
it could be bigger or much smaller, I don't know. I'll give you now examples. Okay. At the end of this talk, I'll get to very simple gauge theories, like deconfined critical points of the sort we heard about, but even simpler. And I'll try to maybe give you an argument that actually we don't seem to find any line operators. Okay. So there could be much fewer or much more, we don't know.
Okay. Thank you.
Do you have in mind the line as something like externally imposed or like product of operators along a line?
I'll talk about the ways you can construct it. Okay. So I'll talk about lines which are more of the Conda type, which have some external degrees of freedom coupled to the bulk. There are also lines of the pinning type, talking condensed matter language, which are given by integrating local operators. I'll talk about many constructions. Here, it is completely abstract, and it applies to all those constructions you have in mind.
Okay.
How you actually construct lines in a Lagrangian field theory or on the lattice is a different question. I'll give you several ways you can construct them and implement it. Okay, but so far it's very abstract. It's just, and of course, the reason that you should care about it in condensed matter language is because in condensed matter we think about a Hamiltonian, we take a slice, and then it's a point. So we have our lattice, and typically, well, a line operator is some impurity that's maybe just localized on a few lattice sites. So you could imagine constructing many types of impurities localized on several lattice sites. They correspond to line defects. And the question of whether it's a conformal line defect or it flows to one is a question about whether this local perturbation dies off when you renormalize it, when you do spin block transformations. So it's a question pertinent, obviously, to condensed matter and to high energy physics. Now, when you give an explicit construction of a line defect, it could be through some, well, whatever construction you have in mind. It could be on the lattice, it could be in the continuum. It's not guaranteed that it's conformal, of course. Like any QF, this is like a QFT in one dimension on the line. It can flow, so there is an energy flow. So there is some infrared line defect, and you give there is some UV definition. Okay, there is some UV definition. Could be on the lattice, could be on the continuum, and there is some infrared line defect, and this infrared line defect can be. So there are three options for it, as far as I can say. Like in bulk RG flows, what could be the infrared limit of an impurity or a line defect? Well, it could be a conformal line defect. Could be some interesting fixed point of the renormalization group flow. So it could be a conformal line defect. When I say conformal line defect, the condensed matter people would say conformal impurity. I have to go back and forth, so I'll be mixing up those languages. So it could be a conformal line defect. That's one possible infrared scenario. It could be, I mean, a non-trivial one. Here I meant a non-trivial one. It could be trivial, completely trivial. That's this case, when there is just nothing there. That corresponds to the situation that you put some impurity, you do some renormalization group transformations, you go further away, and suddenly there is just nothing there. No correlation functions seem to say that there is an impurity. It could be trivial, and there could also be maybe something exotic in the infrared. I don't know if I'll have time, but in one of the papers with Gabriel and Mark, we showed an example where the infrared is a kind of exotic. It's a never-ending RG flow. It's probably a pathological example, but I'll mention it maybe.
Is it ever possible that the impurities kind of grow in size and infect the bulk, so they change the bulk?
Yeah, this is like maybe this case. You would classify it here. Usually, when you do RG transformations on the local perturbation, you expect that it would remain local, and the data is about whether some operators in the bulk that are, let's say, distance d, they might have some one-point functions that go like some power of d with some exponent. This would be some interesting exponent, and if this coefficient is non-trivial, you could say that indeed this operator sees an impurity. So when the impurity becomes trivial, this coefficient goes to 0. The scenario that you mentioned, that it's kind of taking over, might be slightly outside of this framework. But that would be a very exotic scenario. Typically, you would expect that it flows to a conformal line defect with some coefficient A, some exponent.
By locality.
By locality, yeah. But David is right that there are pathological scenarios that the impurity could somehow grow spontaneously. It's very pathological, I must emphasize. It never happens in interacting quantum filters.
Or it forces the surrounding CFT into a different phase.
Yeah, but that would be, that's right, but that means that the surrounding CFT has to have a degenerate phase.
Yeah.
And it's very rare. Like, yeah, CFTs don't have degenerate phases nearby.
Yeah, at least at Mac you have bulk which should be sensitive to changing.
Yeah. So this is very exotic. This is exactly what David mentioned. It requires exactly what Julian also mentioned. It requires some kind of degenerate phase. I'll show you an example. We believe we understand when this happens. So just, this is not a typical scenario, and it will not be a typical outcome of any impurity you would think about.
Sorry to we have the conversation. So suppose I have a CFT and I turn on a relevance operator in some localized.
Yeah, that's an example.
I think of this as my.
Yeah, it's going to be one of the main.
Okay.
That's it's going to be one canonical way you can construct line defects. Turn on.
Then I'll just let you go.
You know, all the QFT books are about integrating local operators over space-time. You just imagine integrating it over a small region of space, but extended in time.
Yeah.
If it's integrated over a region of space-time, then it's not. It's just a local operator. But if it's integrated on time, small region of space, it's a canonical construction of a line defect, and you have to analyze the infrared. I'll talk about it. I want to make another comment. I'll just make general comments about symmetry. So, when we study local operators, one key ingredient is that they transform in linear representations of the global symmetry. So, the local operators of a theory, they transform under G in linear representations. So they form ordinary linear vector representations of the global symmetry G. You can ask, let's suppose I have the space of line defects. I have my conformal line defects, Li are conformal line defects. What should they do under global symmetries? So here the answer is that it's a tad more complicated than the answer for local operators. The Li transform under linearly under a central extension of G, where G hat is a central extension. Let me just say it in a different way that's more mathematically kosher. So Li transform under G projectively. In other words, they're almost representations of G, but not quite. There could be some phases. And
sorry, does that mean the local operator is stuck to the line transform projective G?
yes.
The lines themselves.
Yeah, let me just make it more precise. So, yes, you're right. What I should say, to be completely mathematically precise, is that once you pierce your space-time with a line, and now you have an impurity, you have a Hilbert space. You have a Hilbert space on your three manifolds, sigma. Let's say we have a Hilbert space on sigma. That Hilbert space is in the projective representation of G. That's the general situation. Okay. So the Hilbert space in the presence of the line is in the projective representation of G. The set of lines itself is transforming in a linear representation of G. But the lines that are fixed under the action of G might induce a projective representation of the Hilbert space. Okay? That's the most precise version of what I want to say. In other words, intuitively, you could say that defect operators are in projective representations of G. So that's the same as saying that defect operators are in projective representations of the reps of G. Okay. So symmetry is useful, but it's a tad less useful than in the usual case. And now I'm going to go over constructions. I'm going to go over how would you construct line operators. So people who do quantum field theory in Monte Carlo, spin chains, of course, they can invent millions of ways of coupling, of doing something on a few lattice sites and coupling into the bulk. But roughly speaking, you can think about three distinct procedures, all of which are implemented already in examples in Monte Carlo and also in nature. So there are three different procedures I can think of. One is what David said. We just integrate any bulk operator. We take x equals x naught. That's where our impurity is going to live. And we integrate any bulk operator over time. Since it's integrated over time, it changes the theory. So this is something we add to the action. How is it implemented in a spin chain? You can think about, in QFT, you can think about every operator as associated with some coupling constant. So you can think that this corresponds to turning on the coupling constant only at a few lattice sites. So if you are doing a spin chain, this could, let's say, turn on the magnetic field. But not everywhere, just on a few lattice sites. So that's a completely different thing than just turning on a magnetic field everywhere, which is an ordinary deformation of the theory to a massive phase typically. You could turn on a magnetic field on a few lattice sites and see what happens. Now you can do RG transformations and ask, does the magnetic field go to 0 or does the magnetic field go to a fixed point? So that's the question of whether it flows to a trivial phase or a conformal phase. So there could be some coupling here, and you need to understand the infrared, renormalize it. That's one construction. Condensed matter, people call this type of construction spinning fields, because you are like turning on some external fields on a few lattice sites.
What do they call it?
Pinning.
Pinning.
Yeah, it's like the fin. That's one construction. Another construction is that you have some quantum mechanics that leaves. So let's say that you just remove one lattice site and you put some quantum mechanical model on that site. Could be any quantum mechanics that you can imagine. And quantum mechanical theories have operators. So you take an operator from the quantum mechanics and you couple it to some bulk operator. And then, well, you integrate the whole thing over time. So here you just introduced new operators that live only on the line. Those are operators that are associated with this quantum mechanics, and you couple them to the bulk. This problem in condensed matter you would think more like Kondo. Because why was Kondo? Kondo historically was a problem where you removed one lattice site from spin a half chain, you put some spin s degrees of freedom rather than spin a half, so you have a bigger Hilbert space at one point, and you couple them to the bulk via some coupling that preserves the nice symmetries. So this is called pinning, this is more like Kondo. And then there's the final.
Sorry, question.
Yes.
In the second case, I guess you're thinking of the exponentiated version of that?
Yeah, it's always in the exponent.
Also in the first case?
Yeah, it's always in the exponent.
Or you don't allow them to be what here?
Just
like that.
This is a modification of the theory, so we exponentiate.
Okay, but you could also consider that. I think that's what Philip Argyros was about. So you could consider line operators which are not exponentiated.
Line operators?
Additive operators.
Well, if
Anyway,
you don't
you're not
exponentiate it,
consider-
if you don't exponentiate it, it's a correlation function in the original theory. If you exponentiate it, it's a different theory with an impurity, with a different vacuum, blah blah.
Okay, so that's what you're considering.
Of course, once you exponentiate something like this, you could start treating it perturbatively, where it boils down to correlation functions in the object in the theory without an impurity. But the full theory is with the exponent. And in particular, that's why these couplings get renormalized. If you don't put them in the exponent, they won't get renormalized. Once they're in the exponent, we start lowering it. We must correct the couplings, and there's RG flow. It's just different theory once you exponentiate.
This is like another way of saying you modify the Hamiltonian.
You modify the Hamiltonian in a condensed matter language, indeed. And that's why you need to renormalize. So here there would also be typically some coupling constants. Here there will be some other coupling constants, presumably, and they could all run. And there may or may not be a fixed point. And remember that the bulk is always conformal in this dog. Okay, and the final way, which is perhaps the most, these are kind of straightforward. The last way is, again, you start from a quantum mechanics Lagrangian, but now you assume that this Lagrangian has some global symmetry, just quantum mechanics. A global symmetry, let's say U1. And you assume that the bulk CFT is also a gauge theory. So it's some kind of Lagrangian CFT with a gauge field. And then what you do is you take the current, the charge density in quantum mechanics, and you couple it to the gauge field. So this is the bulk gauge field, the zero component of the bulk gauge field, and this is the charge in quantum mechanics, the charge density. So you're like declaring that charged objects on the impurity are basically sources for the bulk gauge field. So this is what we call, of course, Wilson line. That's Wilson line, yeah? We call it the Wilson line. Condensed matter people call it a charged impurity.
Here you're summing, maybe, depending on how you choose the quantum mechanics, you may be summing over representations of this. I mean, depending on what your Hamiltonian...
This quantum mechanics has some Hilbert space.
Yeah.
And the Hilbert space transforms under some global symmetry G, and that Hilbert space becomes a source for the bulk gauge field.
That's right.
If you don't like my choice of quantum mechanics because the Hilbert space is too large,
Yeah.
or it's an reducible representation of G, I invite you to find the smaller quantum mechanics. It's up to you. If the Hilbert space here is reducible, you would say it's a non-simple Wilson line. That's fine. It's as good as anything. Okay. So this is what we call Wilson line. They call it charged impurity.
Isn't Wilson line usually a static charge, like particle Wilson?
Yeah, it's static. It's at x equals x now.
No, but also no time.
Huh?
No.
A Wilson line is a
no,
charge
not
impurity.
dynamical. The charge is not.
It's not dynamical.
changing
It's
in
at x
time.
equals x now.
And
I put
J
the charged
naught-
impurity at x equals x naught. It's not
But
moving.
your J naught is quantum mechanical degree of freedom.
Of course, that's what that's all. But that's just an internal degree of freedom. Imagine that this is a non-abelian gauge field. Sorry, I must not. What is the question?
Well, I thought like Polakov-Wilson line is like a static charge insertion.
It's static. It's at x equals x naught.
But not static in space. It's localized in space, but it's not changing in time.
This is not changing in time. This Lagrangian is time independent.
I think
okay.
in the abelian case, there's very little happening in the abelian case. The J naught becomes a number. Is that correct?
It's literally if you take a charged impurity,
Yeah.
take graphene, bring a nucleus. This is how you describe it.
Okay.
I think less of this is worried about extra degrees of freedom living on the Wilson line.
Well,
But they don't.
When you integrate them out, you get.
But that's necessary.
Time
That's necessary.
order,
If the gauge field is the bulk is non-abelian, then this gauge field is in an adjoint representation, and this current would be the. So it's necessary that the probe charge would have internal degrees of freedom. If it's SU2, it has to be a representation of SU2.
Okay.
If it's U1, then you're right. Maybe you had in mind U1?
Yeah, that's what.
In the U1 case, this is a very interesting quantum mechanics with exactly one state. So it's not doing anything. It's the unit operator. This is the unit operator. It's just a C number. And it boils down to exponent of IQ A naught. This is in the pass order integrated over time. That's in the abelian case, which is actually the only case I'll talk about in detail. But it's just a special case where this is the unit operator, this is the C number, Q, the charge of the single state in the Hilbert space. But if you want to couple to SU2, then you have to have internal degrees of freedom. Okay, so these are three constructions you can imagine. There might be others, but I'm not familiar with them.
You don't want to consider just setting boundary conditions on the line?
Yeah, probably these are all special cases. All of those three are special cases of the correct way of doing line defects, which is to find self-consistent boundary conditions for the bootstrap. But who knows how to do that? I mean, you can think about this one-point function as a sort of a boundary condition. You just declare that one-point functions in the bulk are going to decay as some power of distance with some coefficients.
I see. You can do it
But
in free theories.
this is called the boundary condition. But who knows what is the set of consistent boundary conditions? This is subject to some nonlinear bootstrap equation. So in free field theory, yeah, you can write boundary conditions, and I mean that's how we think about many of these constructions as actually boundary conditions with a UV cutoff. So that's why we have a UV definition with some cutoff, but in general it's too abstract too.
So how about a 12th lines, for example? That's not any of these three, is that right?
It is for the dual gauge field.
Okay.
But the best way to describe a Hooft line is via what David said, as a boundary condition. So you could force entry if you want for the Hoof-line aficionados. Yeah, the best way to describe Hoof-line is to say that you remove a part of space, and in that part of space you have a prescribed magnetic flux, which is a boundary condition. So you just declare that in the path integral, this is going to be some integer. Okay, let's say in the abelian case, you could say that I introduce new boundary conditions into the path integral, where around a very small sphere of size epsilon, this must be obeyed by every configuration that I sum over the path integral. So that would be a Hoof-line, it's like a boundary condition. Or you could source it by coupling a charge to the dual gauge field. Slightly non-local, but okay. Okay, so this is just a general introduction. Yeah, I think in principle very little is known about infrared of various line defects, even in very simple conformal filters. And I will try to go over some examples today. So, I'll now talk about two non-perturbative constraints on the infrared. Two non-perturbative constraints. The first constraint will be very hard to prove, but I'll state it. The second constraint will be trivial to prove, and I'll also, and so I can do a more honest job. But they're both completely, always completely correct if you have a unitary local model. So the first constraint is the following. So I've been talking so far about line defects that are extended in time in Minkowski signature, because that has a very natural Hamiltonian meaning. But let me switch gears. Let's go to Euclidean signature. And we can also consider closed lines in RD plus 1. And now this will have a radius R. So I'll just make a few comments about the expectation value of a circle. So let's call this expectation value L as a function of R, where L is the line operator. You might be worried that this expectation value is slightly ambiguous. Well, you could do it naturally in statistical physics. If you have some model with a nice Euclidean interpretation, you can even compute it on the lattice. But well, if you can make a circle, it's a slightly ambiguous observable because there are divergences when you compute partition functions. But the divergence here is very mild. The theorem, well, it's a statement or lemma, that the only divergence in this object is an exponential of an unknown coefficient that is scheme dependent times something linear in R. So you can compute this object, but you might miss this kind of contribution would be ambiguous. So to fix that, we define something that we call the entropy, the defect entropy, which takes care of that ambiguity and removes this coefficient C by applying the differential operator 1 minus R ddr, or log L as a function of R. So this is now manifestly cooked up in such a way that this coefficient C drops out. And the claim is that this is completely scheme independent and therefore can be also measured on the lattice in principle. However, it's not a very obvious observable to measure in the lab, because how are you going to make a circle? You cannot go to Euclidean signature and make a circle. Yes?
So is that like a entropy, something like that?
I don't, how do you see the connection?
Like the form of the formula, also the parameter R. Is there any particular limit when you take R going to 1 or something?
No. R is the radius of the loop. And I study it as a function of R. And it's an interesting, R is an interesting parameter because R going to infinity probes the infrared, and R going to 0 probes the ultraviolet. So for me, this is like a function that interpolates between the infrared, ultraviolet and infrared. And in particular, if the line is screened, it's not a bidirectional statement. If it's screened, then S at infinity must be 0. Because the unit operator expectation value is 1, and log of 1 is 0. So S is 0 for the trivial defect. So S provides also a nice gadget that allows you to diagnose a screened defect at long distances, because it has to go to 0. If, on the other hand,
It's not a Reinian, well, I don't think it's a Reinian either, but it's similar to what Mark and Hong did for this disentanglement.
it is true that the entanglement entropy also is subject to various divergences, and Mark and Hong have a paper applying similar differential operators to cancel those divergences. You're completely right in that.
Can you use also S to distinguish between area and perimeter log?
No, this is a CFT in the bulk. I have a CFT in the bulk, so it's always perimeter. It's a slight, what I call screening is not what's called screening in the QCD literature.
I see.
Screening in QCD is perimeter versus area. Once the bulk is conformal, that's not relevant because there is no energy scale. The distinction in the bulk, when the bulk is conformal, screening means trivial line. Non-screening means a line defect that has these interesting one-point functions that decay with the distance. They're all perimeter. But the question is if it's an interesting perimeter or a non-interesting perimeter. So this is a non-interesting perimeter because if that's the only thing that you have, it's a trip. It's a counter term, you can remove it. But if S at infinity is non-zero, so it's a slightly less trivial perimeter though, then of course it's a non-trivial defect, which is probably conformal, non-trivial conformal defect. So why is this function S at all interesting?
Is the sign of C at all fixed or?
Okay, Tin asked a very good question. It turns out that S in the infrared for many conformal defects can be negative. S equals 0 is trivial screened. S negative is a non-trivial conformal defect, and also S positive. But there are many examples of this. Okay, now why is this function at all interesting? I could define a million other functions that cancel this linear dependence.
Sorry, can I ask, isn't it just a number in a CFT, right? This
yes, if you have a line defect which is already tuned to a conformal point,
okay,
then S becomes a number because it's essentially R independent.
okay.
So S shave, sorry, I just said a word in Hebrew. S equals some number
Okay.
for conformal defects. But if your defect is not conformal and it's undergoing some RG flow, then this would behave non-trivially with the radius.
Right. Even if the bulk is conformal, that can happen. Is that
Oh
correct?
yes, because as I said, for instance, take a conformal bulk,
Yeah.
do any of those constructions, typically there will be a RG flow of the Kaplan constants. And this would be reflected by some R dependence of the defect entropy. So why is this function at all interesting? No, I don't think so. It's a partition function, it traces over everything.
So that's L.
L? L can transform, yes. Yes, yes. I mean, some symmetries would take a line defect or a different line defect. So yeah, it kind of transformed, but...
So if L transforms and S doesn't transform.
I mean, S is associated to a concrete line defect. So it transforms to that extent. But for every conformal impurity, you have some value of S.
So, like, I'm guessing that probably you'll be going through this example, but like in condensed matter and the type of, well, what you said, tuning defect, you can have a situation where it disappears effectively at long distances.
Yeah, that's the case where it's called screen. That's what I call screen.
And that's like people say healed, it's healed.
Yeah, healed screen, yes.
Or it may actually, like in 1+1, it will separate, it will cut the system into two non-talking parts in the...
Well, that can only happen in 1 + 1. In 2 + 1, an impurity cannot cut the system into two parts.
Yes. But
in 1 + 1 it can, yes.
In 1 + 1, that S infinity would be, this would be detected by this...
in 1 + 1, when it's completely healed or screened, you would find S = 0.
Yes.
When it breaks the system into two parts, typically this is the case.
Okay.
Typically, not
So there would be
this is a
some-
conjecture, by the way. There is a conjecture of, oh my god, I forgot the name. Jared Watts. Jared Watts has a conjecture that at least in RCFT, this is a signature for cutting the space into two.
Why is it called entropy? Does it have an interpretation of entropy?
I'll talk about it in a sec. First of all, why am I even telling you about this function? It's a random thing that's hard to measure. Even on the lattice, probably not easy. So the reason is that there is a theorem that it's monotonically decreasing. It's always true, it's non-perturbative, and it provides a very interesting constraint on our G flows. So this is why I'm telling you about it. There is a non-trivial constraint on any RG flow, but this must be true. So this, as you'll see, this actually leads to very immediate implications for various defects in condensed matter systems. I'll use this to immediately prove that some of those defects have to flow to non-trivial fixed points. And this answers some long-standing questions in condensed matter. Maybe 10 years, 15 years. Okay. So this is a non-perturbative constraint. That's always true, and that's why it's interesting to consider this option. This is constraint number 1. What did you ask?
I asked why is it called entropy? Is there an interpretation as entropy on the line?
Yes, now I'll say some things about this. In the 1 + 1 dimensions, this is indeed the case. So in 1 + 1 dimensions, this is only true in 1 + 1 dimensions. You have this impurity. You can heat the system up to very high temperatures. You take very high temperatures. Then the entropy of the system is extensive. This is the actual thermodynamic entropy, high temperature. It's extensive. It has one contribution that goes linearly in the size of the system, which is proportional famously to the central charge of the system over 6. And then there is another sub-extensive contribution, which is exactly little s. So in 1 + 1 dimensions, this quantity, which is defined at 0 temperature, is actually the correct sub-extensive contribution to the high temperature entropy. So it captures some density of all the states near that impurity, basically. The high energy density of states. But that's only in 1 + 1D. In D + 1, it's unknown what is the connection to any entropy. But, well, one can speculate some entanglement entropy. Okay? Yeah.
Again about confining gauge theories, the S is negative infinity.
I'm talking only about conformal theories in the bulk.
Well, you could start with some CFT, some kind of Banks and perturb it in the confining regime, and you could ask, how does S...
Yeah, you could do that. The proof of this is for conformal bulk. So I don't know what happens to this. This is proven under the 3 assumptions: locality, unitarity, and conformal bulk. What happens beyond that, I have no idea.
And back to this question about entropy, so like canonical example, Kondo effect, where I guess antiferromagnetically coupled, where impurity survives at infrared and there is like log to entropy.
Yes, this S is equal to log of, sorry, this S is the log of the number of states.
Okay. That survive
that survive at long distances after the RG flow is implemented. So you have an impurity which has 2s + 1 degrees of freedom in Kondo, and some number n survives at long distances. Typically, the number of n that survives at long distances is smaller than the number of the UV. This. And this is what appears in the thermodynamic entropy at high temperature. in d+1 dimensions is not known. But we very strongly believe that it's an entanglement entropy of two impurities in an APR state. It's probably true, but it's not been proven. Okay, now the second constraint on the infrared. The second constraint on the infrared has to do. So this was constraint number 1, and constraint number 2. I think if you don't know much about higher symmetries, you can skip the next 5 minutes. Just I won't actually use it in any of the examples today. But the statement is that if the line defect is charged under one form symmetry, okay, I'll make two assumptions. One is that the line defect is charged under one form symmetry. This is assumption number 1. Assumption number 2, the theory doesn't have d minus. The theory doesn't have. Well, let me just. The one form symmetry charges. The one form symmetry charges can be cut open. What does it mean to cut open? What is a one form symmetry charge? It's a surface of dimension d minus 2, some abstract surface. I don't know how to. Well, I'll draw it in 2+1 dimensions, so it's a line. It's a topological surface, okay? It's an operator which is defined on a surface and it's sensitive to the surface only topologically. I'm not going to be able to explain what one form symmetry here is, but anyway, it's a surface which is topological of dimension d minus 2. If it can be cut open, that means that if there are ways to make it end on something, that's a one form symmetry that can be cut open. You can ask, is it always the case? No. Some one form symmetries cannot be cut open. But the one form symmetries in Yang-Mills theories in 3+1 dimensions can always be cut open. And also, most of the cases you know in 2+1, the one form symmetry surfaces can be cut open. In AVGN theory, or if you confine critical points, this can always be cut open. So if these two assumptions are satisfied, that the line operator is charged under one form symmetry, and the one form symmetry charges can be cut open somehow, you can derive a corollary, which is that the line defect cannot be trivial in the infrared. Trivial or topological in the infrared. Okay. So in theories with one form symmetry, roughly speaking, the statement is that line operators that are charged cannot become completely trivial.
How do you cut these open in Yang-Mills theory?
Like the electric one form symmetry surfaces can be cut open by putting a Tuft line at the endpoint. They end on improperly quantized Tuft lines. So SUN gauge theory has Tuft lines in the adjoint. Those are genuine lines, but the Tuft lines in the fundamental of the dual group are the endpoints of the one form symmetry surfaces.
These surfaces become the Dirac string.
Yeah, the surface is just the Dirac string. That's why it's topological. So anyway, in theories of one form symmetry, this is a very strong constraint. You can even apply it to metals. We talked about it with Max a few months ago. You can ask about metals where the electrons have charge 3, so there is a one form symmetry, and you can ask if the nucleus of charge 1 will be screened. The answer is no. Even though it doesn't matter, the answer is yes, and the answer is no. It cannot be screened because of this constraint. And it's not screened because of these Friedel oscillations. There are some long-term effects of this nucleus that never really die. Yeah.
What about like charge 1 Wilson line and a charge 2 Schwinger line?
Yeah, I'll talk about it if I ever get to it. And we kind of know the answer already. But in a metal,
Isn't that topological?
huh? The bulk will be CFT. I'll give you an example where the bulk is CFT, where the propagating degrees of freedom are charged 2, and you put the charge 1 Wilsonite. It's not screened. Even though in condensed matter for further surfaces people say it's screened, there's Friedel oscillations. And so this nucleus is never completely screened. So this subtle Friedel oscillation saved the day, I believe.
Metal,
It's not been shown, but we believe that the Friedel oscillation saved the day.
but metal is not a CFT.
Fermi surface is not. A Fermi surface would satisfy everything I need for this statement. A Fermi surface would be okay.
What is the exact constraint on the bulk dynamics you need for this to be true?
For the cutting open,
No, I think I'm a little confused because I thought I know theories that flow to just TQFTs that satisfy these two properties.
the bulk is conformal in this though.
Okay, so but that's
I'm just tuning the bulk to a fixed point. You cannot
but,
stop me from
conformal with, I guess, non-zero central charge. Is that
no, this would still be true even in TQFT. If the bulk is a TQFT, because everything I say would still be true.
don't L's flow? In
Yes,
that case,
but
doesn't it
the
flow
problem
to?
is that in TQFTs you cannot cut open the one-form symmetry surfaces. Think about Z2 gauge theory. In
Right.
4 dimensions, it has a one-form symmetry,
Yeah.
but it cannot be cut open
I see,
because
okay.
Z2 gauge theory has a two-form symmetry as well, not just one-form symmetry.
I see,
So
I see.
the
Okay.
two-form symmetry prevents this from being cut open.
Okay, okay.
So actually, there's no contradiction.
All right,
This is
absolutely.
always true.
Okay, thank you.
Maybe the design should not be trivial, but this doesn't mean that the gauge field could not. I mean, the line may not be trivial with trivial gauge field. It's very important to
Yeah, I'll just. If you want, I can talk. We can get to the Schwinger model. Is a gap theory, not CFT. Different discussion. It has two vacua. So the reason that it's not complete, the reason that these constraints are obeyed in the Schwinger model into this because there are two vacua. So that once you place this defect, you've changed the world forever. So it really cannot. It's really not screened in the Schwinger model. People say it's screened in the literature. It's not true. It changes the vacuum. No, but it changes the vacuum. This is the opposite from screening. It changes the one-point functions of local operators arbitrarily far away. So it's definitely not screened, and that's how you save the day in the Schwinger model. In metals, you save the day by Friedel oscillations, I believe, though we haven't proven it.
Can I ask you, when you don't have a one-form symmetry in metals, you have Friedel oscillation. Would you say that's not screening either?
I don't want to say something about it. We believe, maybe Gabriel doesn't, I believe that Friedel oscillation is the key of
Are they
why
different when you
why
have
it's not screened in metals.
Are they different when you have a one-form symmetry and when you don't?
Not so much. Not so much. That doesn't mean anything.
Just
So it's not a contradiction. This statement is only in one direction. I have to think about it, but I believe this is the key point. If there is no Friedel oscillations, then this would be violated. It's obviously mathematically a theorem.
Somehow we're using the word screening wrong then. Screening comes
No,
from
screening
metals.
means that you have to be able to take a topological surface, put it arbitrarily far away from the impurity, and observe something.
Yeah.
So if something is exponentially decaying, like if everything was exponentially decaying, that would obviously be not possible.
Like screening means
Ba-
what happens in metals and anything
No,
else?
but basically you do not, the usual screening, there is a long-range Coulomb interaction, which in a local theory you are not including. You do not have, you have short-range interaction. So when you
I think,
cannot
I
screen-
think for bulk CFT, we can talk about metals, Fermi surfaces, or Schwinger models. Obviously, this is satisfied in my opinion. In Schwinger model, it's a one-point function that's activated very far away. In metals, there's Friedel. I'm talking about CFTs. And in CFTs, this just means that there are non-trivial one-point functions, or some local operators, with non-zero A coefficients. Okay, so these are two non-perturbative constraints. And now I'm gonna bombard you with examples, which are, I mean, it's all many conjectures about dynamics, which should be checkable on the likes. I'll start from DON models, and then I'll go to gauge theories. It's a natural point to take a break. Then I'll do 20 minutes of ON models and 20 minutes of gauge theories, and that's it.
Okay.
If that's okay.
Break. So how long would you like the break to be?
Whatever.
So we say 5-minute break then?
10 minutes.
10 minute break? 10-minute break. Okay. We reconvene at 5 past. So the point that everything that's true that's just close to a TQFT in the IR, probably all of those I can't. I see.
Yeah,
Okay.
you kind of know it's true because I think you really deserve grade, some dimension, whatever. And so they can't otherwise the grade is
Actually, I think I'm confused. I thought that
Did you have
I was measuring the grading. But I guess
yeah,
this is dual symmetry. This is the charge operator for the other one. That's the idea.
I see.
I think I agree with you. I also computed how many units
Okay.
and then I get it. Yeah.
All right.
Yeah.
Good. Maybe we can try to discuss it.
Yeah. If we have some more. Yeah. So if you have time tomorrow, then tomorrow afternoon we can have
Is nice. Yeah. All right.
free time.
Okay.
So, yeah. That's
Okay,
great.
good.
That's great.
But can you remind me what so in the context of 1D Latinger liquids, the screen cases where you have healing, does it require like interactions that are basically free fermion is a Latinger liquid, of course, but it has some specific Latinger parameter, and I don't remember. It's for that Latinger parameter, it's not screen.
I don't remember.
Okay. Well, because for free fermions you have free
Yeah,
Dell oscillations, so if you
Yeah,
insert
I think
it will.
my feeling is that for the free fermion, it's not screen.
Okay.
Just because
Yeah,
side by side
if
has dimension
I-
1, you integrate it.
Yeah, if I remember correctly, that healing or breaking depends on the Latinger
Yeah, it's not
parameter.
screened for the free fermion because you can integrate psi group psi,
Mhm.
and that's an exactly marginal operator. on the
And
defects.
and examples of CFT would be like 2D Dirac
Yeah,
fermions.
I'll talk about this example
and
soon.
the defect, and there is a texture which decays as like, I don't know, 1 over R to some power.
Yeah, I'll talk about this example actually.
Okay.
U1 plus an F fermions,
Mhm.
where you put the charge in purity.
Mhm.
Charge 1, something.
Mhm. Yeah, one knows how the texture decays. Like I.
I'll mention this example.
Mhm. Some of the
say the symmetry can be caught up, is that another way of saying that it can be gauged? So we're going to the
exactly.
other.
Yeah, exactly. That's equivalent to being able to gauge the one-form symmetry.
Get the
100%.
magnetic one.
Yeah, 100%. It's the same condition.
Alright, thank you.
I think it's the same. You have to ask a mathematician. Somebody knows, but I think it's definitely
so if
necessary.
you're going from the electric one-form symmetry to the magnetic one.
If you can cut it out, if you can gauge it, definitely it's cuttable. If it's cuttable, whether it's gaugeable, you have to ask somebody more knowledgeable. But I think the answer is
Did you
yes.
say that in the Yang-Mills theory you have the tooth line and it ends on a
Yeah.
Dirac string?
The Dirac string is the
Yeah.
surface and
Yeah,
it
so
ends on a tooth line. So
it
it's
can be in a vase screen.
yeah, but we know that this is true. You know that you can gauge, one-form symmetry in 4D Yang-Mills. You can convert SUN to PSUN. You can convert PSUN to SUN. So we know it's cuttable. It's all fine. In 2+1D, there are examples where it's not cuttable, like in TQFT, 2+1D. Yeah, in principle, in many examples, it is cuttable, and it's, I believe, equivalent to the condition of being gaugeable. But I don't know if it's theorem. I just think it's true. Yeah.
Oh yeah, sure. Okay. All right. Ready to get started again, Zohar? Should we get started? Or?
Oh yeah.
Okay. Okay. Welcome back. We're starting.
Okay. So I promised to bombard you with examples now. Some of this stuff is proven. Some are slight extrapolations or our conjectures. And I'll tell you what. So first I'll start from ON models, which are canonical models for magnets. And then I'll go to gauge theories, where we found a vast number of very interesting phenomena about various line defects. But I'll start from the ON models. So you remember there are three ways of constructing line defects. So this would be the first. You'll start from the Lagrangian of the ON model at the fixed point. So I'm tuning to the Wilson-Fisher fixed point, where there is some non-zero G star, and you can realize it from a spin chain in myriads of ways with interferomagnetic spin chains. But in particular, O3 is very easy to realize, and O1.
So this is 1 plus 1.
Everything is going to be in D+1. Mostly, of course, the interesting case is 2+1. That's where experiments are done. So that's where I'm going to emphasize more. Okay, so this is the setup, and the line defect is you integrate phi 1. You put an integral of phi 1 in the exponent, integrate it over time, and the way you physically realize it in a spin chain is that you put a staggered magnetic field over a few lattices, and you'll see what happens to this external magnetic field at long distances. Does it get screened? Does it not get screened? So it's a very hard non-perturbative problem because it's it's an interacting field theory. How do you compute what happens to the magnetic field at long distances? And here, this is where this theorem about the defect entropy comes is very useful, because here you remember that in the bulk, the scaling dimension of the order parameter phi is very close to 0.5. It's at like 0.51, 0.52, depending on n, very weakly. So this h is irrelevant. And so the way to think about this defect in the abstract world of line defects is that we have a trivial line defect in the UV where h is 0 and it's the unit operator. We deform it by a relevant perturbation and it flows to something that we must understand. But because it's a trivial line operator in the UV, the entropy of the ultraviolet, the defect entropy of the ultraviolet vanishes because it's a trivial line defect. And therefore, from the monotonicity theorem, from this theorem, it immediately follows that the magnetic field cannot be screened right away. So you immediately derive a non-perturbative conclusion that the magnetic field cannot be screened. In fact, it only grows, and it cannot disappear all of a sudden.
Sorry, stupid question, but why does it have to be staggered? I didn't quite...
It's because when people like Andreas realize ON models in a spin chain, it comes from an anti-ferromagnetic spin chain. And the order parameter in the continuum field theory is given so the order parameter in the continuum is related to the parameters that they use by something like -1 over the lattice height to the spin. So it's because an anti-ferromagnet order is a staggered situation. So also applying a magnetic field has to be done accordingly. It's very easy to simulate, I believe. So, but anyway, this monotonicity theorem is really applied here with some nice, with a great success. It immediately implies that this cannot be screened. So we must understand the infrared. So I'll tell you what we know about the infrared. It's a strongly coupled problem, obviously. So here, this is the case where I told you. So this is the multi-critical ON model. It's the free field theory. This is just mean field theory. It's not very interesting. It's because it's multi-critical and less universal. But first, let me start from this. This is a case that you can give in a quantum field theory course in graduate school because there is no interaction, and the whole thing is quadratic. Albeit this is localized at a point in space. So you can give your students an exercise to compute the Green's functions. It's a solvable model. And in this case, it is true that S as a function of R goes to 0 and R going to 0. So it is indeed a trivial defect in the UV, as we've anticipated. But bizarrely enough, this is one of those cases that David anticipated, that somehow, in this case, the magnetic field just blows up and swallows the whole bulk. And it actually goes to -infinity. The flow never ends. So this is a never-ending flow. The magnetic field is never screened. It kind of grows to infinity and it doesn't stop. You don't get a conformal line defect. This is indeed equal. Okay, there is no conformal line defect. Now, to be more precise, this is the correct conclusion for any number of dimensions which is below 3 space dimensions. So in 3+1, actually it does stop. But below 3+1 dimensions, it never stops, including in D equals 2, where it's more easy to simulate.
Oh, but just Gaussian theory.
Huh? It's a Gaussian theory. Okay. This is the only case where we have a closed formula for any R for this flow.
No, but it feels
this is a very
from the point of view of lattice statmat, but this is not in D less than 3. This fixed point is not a lattice statmat.
D equals
It is not the spin model, like in D plus 1 larger than or equal 4, the Gaussian theory will apply to yours.
It's a pathological example because there are this. Somebody before said you have to have some sort of degeneracy or something.
Mm-hmm.
This theory has flat directions, so that's probably the reason. Anyway, it's a pathological example. For this case, which is the ordinary Wilson-Fisher fixed point, the celebrated Wilson-Fisher fixed point, S goes to some number S star, which is finite and smaller than 0, consistently with the monotonicity theorem. We don't know how to solve exactly for the infrared fixed point of this defect. It's a non-perturbative problem, but actually following on similar things that Max did and collaborators, you can solve it exactly at large n. We have an exact solution, and we also have an exact solution in the epsilon expansion. These two things you can do. And well, one highlight is the scaling dimension of the lowest defect operator that is neutral under the ON symmetry, ON minus 1. And I'm just quoting it here. It's a defect operator, not a bulk operator. That's why I'll just keep the notation like before. This came out to be 1.5, roughly speaking, at large n, and also in the 3 minus epsilon. This is what it indicates. It's roughly 1.5, while the bulk scaling dimension, as I told you before, is roughly 0.5. So you see it acquires a huge anomalous dimension near the magnetic field. Anyway, we believe that this always has an infrared fixed point. We have lots of predictions about this fixed point in one of the papers from large n, epsilon, from these monotonicity theorems. It's not checked yet, but this part is trivial. This is trivial, this is not checked yet.
Do other components get a different...
Yeah. So this is the simplest defect operator that is invariant under the ON minus 1 symmetry. You can also ask, what is the defect dimension of phi hat, where this denotes the component, which are 2, 2, n. And this is a vector of ON minus 1. This is actually exactly 1. Yeah. Okay.
And these are not dependent on epsilon or n?
It does. These are the predictions in 2 plus 1.
Oh, I see.
Where it's more easily checkable using Monte Carlo. We have the predictions for it, yeah. Okay. This is comment number 1 about the ON models.
Did someone track it? Sorry, I missed
No, this.
No.
There is a paper by Assad, Tolgien, Parisen, where they simulated it. They got something in the ballpark. I think they had like 1.4 or something. Few people tried to, simulate it.
They check correlation functions on just lines of spin operators?
No, you just put this external magnetic field, you do the RG, and you try to compute correlation functions of spin operators away from the magnetic field, and from those you can read out scaling dimensions of defect operators. Okay, this was a class of line operators in the ON models that do flow to conformal fixed points. Now I'll tell you about another class, which is of the second type. I'm just going over all the 3 types of constructions, so to impress on you that this can be actually realized.
Could I just ask one more? So these values you quoted, are they calculations for n equal 2?
This n equals infinity. We have an exact result.
Infinitely, okay.
Yeah, we have an exact result at n going to infinity. We have epsilon expansion results, and we also did some 1 over n kind of thing. It doesn't seem to vary a lot. So we believe that probably when people simulate it for n equals 3, it will be 1.5.
Okay, so and this simulation that you quoted 1.4 was for n equal 3?
N equals 1.
N
N equals 1, yeah.
1.5.
N equals, this also applies in the Ising model. Oh, and also we in 1 plus 1, this problem makes sense in 1 plus 1 too. And there you have an exact result because it's Ising is solvable. So we know everything about the defect entropy, scaling dimensions of defect operators. And then it's 2. This is 2 in 2D, if I remember correctly.
And this, what you call, again, just
in 1D.
To clarify, this in-field theory, if in D larger than 4 or larger than 3, do you get the finite answer?
Yeah. You see, this is problematic. This perturbation is problematic in d bigger than 3 because it's an irrelevant operator.
Oh,
You remember that the scaling dimension of the bulk
I see. Okay.
above 3 plus 1 is bigger than 1. So integrating it on the line is a little bit a suspicious thing to do. You'll start generating counter terms and divergences. It's not well defined. It's still a quadratic theory. You can close your eyes and solve it, and you find, well, the RG flow there is reversed, kind of. You flow to the UV.
Okay.
It's kind of not a good thing to do.
That becomes trivial in the infrared.
Yes, H is trivial in the infrared in that case, and well, we don't know what it is in the UV. It's still going to be consistent, but it's not. This picture is reversed.
Okay.
The UV is, yeah, so. Okay, the next type of constructions are much more similar to Wilson lines. They're also. I'm going to focus again on the LM models. It's another, just to show you the other type of construction. Now I'm going to focus on O3. The O3 model, not generic N. Max has a paper about various ways of doing what I'm going to say a generic N. This is also an example where there is a projective representation. So what you do is, so you invent the quantum mechanics. I'm not going to write the Lagrangian. Maybe I should. So you invent the quantum mechanics, which has a Hilbert space, which is very simple. It's a spin L representation of SO3. And L could be, in general, a half integer. Okay, so L could be a half integer, so 2L is in Z. You just write down any quantum mechanical model, or the Hilbert space is just a single spin L representation. Okay, so it could be a cubic if L is a half. Could be. I can write Lagrangian that does that. Is that necessary? Or?
But why is it half? If it's SO3, why are you taking half integers?
Oh, because I'm going to give you an example that you can couple a line defect in a projective representation of the global symmetry in the bulk.
Okay.
So you can couple a spin a half impurity to the O3 model.
Oh, okay.
Like a fractionalized excitation. So I don't need to write Lagrangian, or somebody wants. Okay. So then on this Lagrangian, there are quantum mechanical operators, which I'll call S, which are in the adjoint of SO3. Those are the charges of SO3. So if you have such a quantum mechanical model, there will be an SO3 symmetry, and there will be just the usual netter charges. So those are some abstract quantum mechanical operators. And then you write a Lagrangian for the defect, where all you do is you just couple these rotation matrices to the bulk phi. You identify these two indices. And A runs from 1 to 3. You could do it for any SON. You could couple some projective reps. As I said, Max with Vishwanath and others said a paper about it. This is a line defect. The way you realize it in the lab is instead of this staggered magnetic field, is you take one side, remove it, and put a spin L. Instead of having spin a half antiferromagnets, you put some external spin L.
Zohar, could you change the marker because that one seems to be expiring? Maybe that black one, that thick black one, how is that working? No.
Can you throw it out on the floor or something?
Yeah, just, yeah.
Second?
Oh, just the ones that don't work, just leave them on the floor so I can get rid of some.
There's a bunch on the board up in this yeah.
Here?
Here, yeah. There's plenty.
Oh. Great, yeah.
Good.
Anyway, so these defects are easy to realize. They're just external spin S that you can couple to the bulk in this fashion. And this is basically a higher dimensional condo, okay? If you're familiar with the condo problem, this is that just condoing 2+1. It's very similar to the condo coupling. Here, the ultraviolet line defect is when, again, this has dimension 1/2, this has dimension 0, so it's a relevant perturbation. Gamma is again a relevant perturbation of the defect, Except that now the ultraviolet is not a trivial line defect, it has 2L plus 1 states. So SUV is 2L plus 1. 2L plus 1. Okay, and it has to flow and it has to decrease according to the monotonicity theorem. And there is a big question, what do you reach a fixed point? Now, this defect can be written in a way that is very similar to a Wilson line. So,
Is it a log?
say again, please.
Is it log?
Yes, I'm sorry, indeed. Thank you. This marker is no good, maybe we'll bring another one. Well, thank you. I will anticipate that.
Just give me those.
Yeah. Thank you. Okay, so where was I? So this is a relevant perturbation. SUV is log 2L plus 1, and then it flows. And you have to understand the infrared. Now, if you can do the path integral over the quantum mechanics. It's the simple quantum mechanical model, and write this line defect like a Wilson line, but with no gauge fields. So you can think about this whole exercise as a preparation for Wilson lines. You have a trace of a path-ordered exponential, and the trace is in the 2L plus 1 representation of SO3 of phi a times Ta integrated over time, and with a coupling constant gamma, very importantly. Wilson lines don't have a coupling constant. This one does. So it's literally like a Wilson line. These are the matrices of SO3 in the 2L plus 1 dimensional array, and these are the bulk scalar fields phi. So you can ask, what is the infrared? Okay. And so this is like a Wilson line in the ON model. Maybe it's a complex solution. You might think it's a Gaussian field theory. How can it be complicated? But the fact that there is this path ordering makes it seems unfeasible to solve it exactly, even for the Gaussian field theory. So even for the Gaussian field theory, there are no certain final conclusions yet. But I'll tell you what we think.
Because it's at the point, couldn't you integrate everywhere away somehow?
Say again?
But it's only along a line, so you could do the path integral everywhere else, couldn't you?
You could do the path integral everywhere else, but then the price that you would pay is that there will be some non-local quantum mechanics on the line, and we don't know how to solve it exactly. There was also recent simulations of this problem by Adam Nahum and others, and he only looked at G star equals 0. We have results also for non-zero for the Wilson-Fisher fixed point, not just mean field theory. And well, I'll tell you what the state of the art about this problem is now. So for G star equals 0, which you might think you can solve exactly, but it actually turns out to be not the case. This is the phase diagram as a function of L. Some parts of it, this is 3 plus 1 dimensions, and this is 2 plus 1 dimensions. So I'm just going to plot it between those two dimensionalities. So there is like a curve, which we found, where here there are two fixed points. One is stable infrared, one is infrared stable, and one is infrared unstable with a relevant operator. And here there are no fixed points, and rather the answer is analogous to that magnetic field that swallows the whole space. So this is the exotic runaway. This is again possible in this model because there is no potential for phi. And here we found numerically, okay, so this part of the story is rigorous, but this part is conjectural. Oh, sorry. Let me plot more carefully what is rigorous. This part of the story is rigorous. Everything inside this, so I should use a different color. It's the color of rigor, not any phase diagram.
Here.
Oh yeah, I have a red color that you banned before. Yeah, so this is the black lines are the phases, and the part that we can rigorously prove is like this, more or less. So we see this nice line, but okay, here we don't know. Where exactly this line intersects, we don't know, but just extrapolating what we did, we find a third. So it seems that every Kondo defect is in this exotic runaway phase in mean field theory in 2 plus 1 dimensions, because L the physical values of L are beginning from a half. So that's what we believe is true. It's up for the simulations to determine whether it's the case. This transition is very interesting. How do two fixed points disappear into an exotic runaway phase? This is an infinite order phase transition, which is very similar to BKT. This is an infinite order phase transition that two fixed points merge and go to the complex plane. This part was verified numerically by Adam Nahum, I believe, recently. And also by Zeitlin in some other, but not numerically. Okay.
Could you explain why flat directions are needed for this runaway behavior?
Why?
Yeah.
We don't know. We just never found them in other theories.
You don't have some story about how the flat directions allow this runaway behavior?
No. Basically, the idea is that if there are these flat directions, putting a line defect can order the field with no much cost of energy. You can go to one of the points on the moduli space of Aqua without paying too big of a fine.
So it cannot happen in lattice.
It cannot.
What exactly did Adam simulate?
Adam simulated this Gaussian filter with this operator.
In which dimension?
Near Adam simulated in 3.99.
It was Weber and Voita, not Adam.
So what did
Because
Adam do?
The one who recognized. Adam did some
Adam just saw this thing analytically also.
Yeah, it was Weber
Okay,
and
yes,
Voita.
sorry. Weber and Voita simulated it, and Adam found the same infinite order phase transition a few months after us. Yeah, okay. Adam Nahum.
So for L equals 1/2 and 2 plus 1, I think we have results for
Who?
that.
You?
Yeah, if I understand you correctly, we did with Subir Sachdev and some other people, we did bi-layer quantum critical system and removed one side, so there's a spin 1/2.
That's different. It's a different line defect.
That's the
That's a line defect where there is a fermionic impurity too.
But if I understood your explanation on the lattice, it seems it should be.
But he has also a spin out impurity.
Yeah, it's not exactly the same. The thing that you're talking about has 3 states, not at L equals a half, right?
Well, no, I don't think so.
In just the Wilson-Fisher. It's just the spin one.
Oh, you did the Wilson-Fisher.
It should be the Wilson-Fisher.
Okay, Wilson-Fisher is a different story.
Uh-huh.
Well, for the mean field theory at L equals a half, we believe is in this exotic runaway phase.
Okay, so you're talking about the mean.
And as I said, it was verified numerically around this area. There is an infinite order phase transition here, where two fixed points merge and go to the complex plane. So here it's okay. Now I'll tell you what we believe is the answer for the Wilson-Fisher fixed point.
In this story, it didn't matter if it was half integer or even integer. Is that right? It's just a smooth curve for.
Yeah, you can solve this because it's a Gaussian filter. You can analytically continue everything in D.
As a function of. Okay.
Sorry, it's not Gaussian. It's a very complicated filter, but you can analytically continue things in D quite easily.
Right, but I meant as a function of L, the integerness of the representation. It doesn't care about the versus.
Not if you do an expansion in L, of course, but it is important at the end of the day that these are finite matrices. Yeah, I think you can analytically continue in L, because at every order in perturbation theory, you're just using some identities of SU2. So I think they're all analytically continuable. Okay.
What was the scheme? Why do you say this is rigorous? Did you do an expansion in something on large L and?
Oh yeah, we do lots of things. This is Gabriel is the world expert in finding small parameters. So here there is an expansion in 1/L. Here there is a double scaling limit, which is similar to what Gabriel developed with Riccardo Ratazzi in his PhD. Here there is ordinary epsilon expansion. It's a huge story. There are some double scaling, triple scaling, ordinary epsilon expansion, and large spin limits. And we did all of them to cover this area. by the way, I should say that this unstable fixed point is non-perturbative. If you look at the at where it appears in terms of this coupling constant, there are two fixed points in this region. The fact that there is another unstable fixed point is not possible to see in perturbation theory using ordinary epsilon expansion. And in fact, it was missed before. In some papers of Subir, they did not see it. And they did not see the transition because of that. It's non-perturbative, but using these double scaling limits that they developed, it's possible to do it now. Okay, for the ordinary Wilson-Fisher fixed point, which is more physical, the phase diagram is the following. We believe that there is just one fixed point everywhere, one infrared stable fixed point everywhere, and there is complete analytic control in some region, which is like this again. So at large L, so one outcome of this work was that at large L, this is now a completely interacting impurity in in the Wilson-Fisher fixed point. But we found a new way of doing an expansion here. So we have actually exact predictions about the large L limit. And amazingly, what happens at large L is that you basically get results which are very close to the pinning field that we saw before. So we claim that some of the critical exponents for a pinning field for O3 will coincide with the larger limit of the contact order.
So what's on the right? Inside is one fixed point? What's
everywhere? This red is just the region of rigor.
Oh.
There is one fixed point everywhere. That's what we believe.
I see. Okay, so everything on the right is.
Yeah, the red is just rigor. This part is what we can show rigorously, and there is one fixed point everywhere. But the main point is that for large L, it approaches some critical exponents of the pinning field model, which is completely different a priori. But it approaches it analytically, and we have some expansion at large L around the pinning field critical exponents. This allowed us to make some predictions also for small values of L by just extrapolating. And that's where this thing
Okay, so that's the one we did.
That's that's what we did. We did some, I remember, rough extrapolation. It seemed in the right ballpark.
Right. So I think I just looked at my paper. I think we got the scaling dimension 0.7 for L equals 1/2.
Yeah, we have basically exact results here. We did some extrapolation.
If we extrapolate, we get close to 0.7.
We got, I don't remember how many percent, but it was in the ballpark. That's all I remember. But the thing to do is really to just go for large L, because there is analytic results, we have analytic predictions. Actually, there are infinitely many operators at large L that become integer dimensions. There is some kind of integrability at large L. And so we have lots of predictions for large L that are analytic, even in 2+1 dimensions. Okay.
You seem surprised that it's the same as the prediction?
It's
reasonable that
it's not. I mean, there is a general expectation in condensed matter that if you put on a lattice a spin in a very large representation, you approach a classical limit, and it stops fluctuating. And when you put a huge spin and it stops fluctuating, it just polarizes as if it were an external magnetic field, because the coupling is SA times phi A. So SA just settles into a direction. This becomes the pinning field. It's not exactly the pinning field because you still have to integrate over possible directions of S. So it's pinning field plus some interesting zero mode that's coupled to it, and it leads to lots of operators of integer dimensions. So anyway, we developed this 1/L expansion. And, yeah, that's the picture for the critical point. I'm going to switch now to Wilson-Einstein unless there are questions about Wilson-Fisher. The charged impurities. I'll do charged impurities in 3+1 and 2+1, where it's more easily checkable again. By the way, this large spin limit that I mentioned here is again similar to something else that Max did about the new the new phase transition in ON models with a boundary, where there is some RG flow from the special fixed, I forgot the names already, to the normal fixed point. It's very analogous, technically. And Max also had some integral over zero mode that decouples in the infrared, and that's analogous to this story. Okay, now Wilson lines. I believe Wilson lines, perhaps for high energy physics, are quite interesting, and for condensed matter, these are charged impurities, and with graphene and with QED in 2+1 dimensions, there are now real experimental prospects of measuring something. So I'll cover first 3+1 dimensions. I'll discuss a billion Wilson lines in a billion gauge theory. That is kind of conformal. It's not exactly conformal, but it's good enough for what I'm going to tell you. So I'm going to analyze the following model. It's just QED with a scalar field. Scalar QED with a massless scalar field. Okay, this is a scalar QED with a massless scalar.
Did you switch the?
Yes, with a massless scalar field.
Okay, just give me everything that doesn't work.
It's QED with a massless scalar field. Everybody knows it's not conformal. These two couplings run a little bit, but this running will be tiny. I'll take the fine structure constant to be 1/1,000,000, and this will be 1/1,000,000, and the running is basically unimportant on any energy scale. And then we'll add a Wilson line with charge Q. Here there is no intrinsic, you don't need to add degrees of freedom on the at the point on the Hilbert space, it's a billion, like we said before. So this is integrated over d4x. Okay, so you might think we know everything about Wilson lines. Wilson lines are just charged impurities of charge Q. What happens in QED if you put a charged impurity? You develop a Coulomb field. This is called the nuke. E squared Q over 4 pi r. R is the distance. Okay, so this is the one-point function for the gauge field away from the charge impurity. If you want to think about it as a nucleus. So a nucleus is like an immobile charge impurity in QED. We have massless scalar fields too. So this is a saddle point. If you just look at the equations of motion of this system, this is a saddle point. You solve the Coulomb law, and you have no scalar field turned on. So this is comment number one. Comment number two is that if you look at this line operator, the charge is quantized because we have a compact U1. And therefore it cannot run. This coupling constant Q cannot run because it's quantized. So based on all the examples from before with magnets, you must immediately conclude that this flows to a conformal fixed point because there is nothing that can even run. This will turn out to be false. So naively, there is a fixed point, and this is the fixed point. Just you can compute now Green's functions in this background. You can solve this as a you can naively solve everything around this background. So we thought, and we computed the defect scaling dimension of the operator phi dagger phi, which is a nice gauge invariant operator to put on the defect and compute its scaling dimension. Of course, in the bulk, the scaling dimension of phi dagger phi is just 2. It's like it's a free field theory almost, because the coupling is 1/1,000,000, and this is 1/1,000,000, so it's 2 plus maybe tiny corrections. But when you compute the defect scaling dimension, what you find is that it's 1 plus square root of 1 minus e to the power 4 q squared over 4 pi squared. You find this exact formula plus tiny corrections. And unfortunately, this becomes imaginary at some point. And slightly before it becomes imaginary, it becomes 1. And at that point, this is a marginal operator. So neglecting it was inconsistent. So
Is the limit you're working at E goes to 0, EQ
yeah,
normal?
so to be precise, I'm taking to make these formulas precise, you can take a double scaling limit where E squared Q is finite and E squared goes to 0. Then you can neglect the beta functions and all this stuff. And this becomes exact. So you see that when people write in textbooks the formula for the Wilson line, it's kind of wrong. There's something wrong about it, because for a large enough Q, there is another marginal operator. So this operator becomes marginal where E squared Q over 2 pi is 1. So we have a marginal operator when this happens. When Q is small, like 1, 2, doesn't matter, it's a tiny correction to the bulk scaling dimension. But suddenly it becomes marginal. So actually, there is a coupling constant. It's just that the formula for Wilson loops was wrong. There is a coupling constant here that we cannot neglect, and it's important especially when Q becomes large enough. So there is a beta function to compute. So that's what we did. We computed the beta function for gamma to understand the true infrared limit of a nucleus of charge Q. And what you find is the following.
Why do you say the formula is wrong? I mean, this coupling will get generated if you want to
Yeah,
analyze
so
the RG flow.
that's
you
right.
have to
So
include it, but
yeah, the
there's
way
nothing-
we write Wilson loops,
it only has quantized parameters, so we might think that's the end of the story, but there is a relevant operator that cannot be neglected. So maybe wrong is the wrong word. But
I mean,
maybe a
you
little
can
bit.
still use it without any coupling.
It will
In
be
the UV,
generated.
It will flow to, maybe there's potential different flows it will flow to, but it's still an operator. It's a good operator, even without extra coupling.
Yeah, it's a little bit analogous to writing QFTs without relevant operators and pretending that they don't exist. So. I don't know if wrong is the right word.
It's incomplete.
Kind of incomplete, yeah. So this logic is, of course, wrong. Okay.
Zohar, if the Wilson line is charged under one form symmetry, in this case, do you have, I mean, gamma has to like come with specific.
Oh, yeah, thank you.
such that you
Thank you, Mohammed. So I forgot to say that
here phi has charge 1. So I intentionally do not discuss the theory with the one-form symmetry. This will be a different story. What I'm going to tell you is just about the theory with the charge 1 dynamical particle.
So what if it has the charge 2? Do you know the story what will happen in this case?
Partially.
I see.
We know half of the story. With the third, we know a third of the story. So the beta function is like, so we computed the beta function, and it behaves like this. Okay, like this, yeah? So these curves, this is for E squared Q over 2 pi slightly bigger than 1. This is what E squared Q over 2 pi is exactly 1. And these are the E squared Q over 2 pi is smaller than 1. So in nature, E squared over 2 pi is 68. Is 1 over 68. So for Wilson lines of charge above 68, you're here. Nuclei above charge 68, you're here. Below 68, you're here. Below 68, you're here. So here, there are 2 fixed points. See? So actually, when we say that when I told you that this was a fixed point, this was also kind of wrong. There are 2 fixed points for small q. So there are 2 conformal Wilson lines, not 1. This is a stable fixed point, and this is an unstable fixed point that can flow to this one. Then they merge, and then they disappear into the complex plane. And when Q is bigger than this critical value, the flow takes you to infinite coupling. So the flow takes you to infinite gamma. For E squared Q over 2 pi bigger than 1, the flow takes you to infinite gamma, and you have to understand the infrared. And there is dimensional transmutation. It's again an infinite order phase transition, and there is dimensional transmutation here. and you generate some exponentially large flows like UCD. So there is dimensional transmutation, and there is some infrared that you have to understand.
What happens for sufficiently small gamma? It flows away. This one is unstable, so it will run away.
I mean, I think that the normalization of what is gamma equals 0 is ambiguous, like in any. I mean, you know, it's kind of
Fine, but
ambiguous.
this is unstable, so it will run away. What happens?
Yeah. Good question. So also here, if you happen to be stuck with a small nucleus at the unstable fixed point, a small deformation can take you to some very unpleasant place.
And what is it? What happens?
Yeah, I'll tell you. I'll tell you now. We analyzed all of this in great detail.
So this is why this is experimentally relevant. Even for nuclei that are not huge, there is an unstable fixed point with some interesting properties, and there is an RG flow between two. So there are two conformal nuclei, kind of.
It will be observable in graphene, because in graphene, E squared over 2 pi over 4 pi is like 3. So you need much smaller nuclei to see this phenomenon. Okay, so I have to answer what happens here and what happens to this.
So I already said, so the bottom line is that there are conformal Wilsonites, but only up to some charge. For larger than that, they don't exist, and they are strict. So our answer is that for E squared over 2, let me write the answer as a table to summarize, and then I'll make comments about 2 plus 1.
I'll write the answer as a table. So so when the charge of the Wilsonite satisfies this, then it's completely screened. So we actually think that the nucleus gets completely screened by some kind of cloud. So physically you have a nucleus with a huge charge. There will be some Bose condensate of this phi. Phi will Bose condense, and it will completely screen the charge. So the infrared is completely trivial with 0 defect entropy. For E squared Q smaller than 2 pi, but bigger than, I think, 4 pi over square root of 3. I might be slightly wrong about that. There are 2 fixed points. These are the 2 fixed points I showed you here. One is infrared stable, one is infrared unstable. And Tin asked what happens if you're stuck at the unstable fixed point and you kick it in the wrong direction. The answer is that it's also screened. I won't write it here, not to confuse the blackboard. But we believe that if you're here and you just, we believe, we show this, that
here you develop a Bose condensate and it's screened.
So by screen you mean
the infrared is not, there is no charge in the infrared. If you make a big surface and measure the electric field in the infrared, like at huge distances, this is 0.
But not only that, all correlations
approach the bulk.
Same.
They approach the bulk QED answers with no leftover trace from the nucleus. This, however, happens on huge scales. You can ask what is the size of the surface? You have to draw around this nucleus to see that it's completely screened. Because there is dimensional, it's an infinite order phase transition with dimensional transmutation. It's actually a huge scale, which is like exponential
of 1 over square root of E squared Q minus 2 pi times the UV cutoff scale. Times the UV cutoff scale in dimension.
It's a huge scale close to that boundary.
Compared to the nucleus size. So you can imagine that the nucleus has some finite size, it's a UV cutoff, and the size of the condensate is exponentially large. You can go all the way to the moon if you're at 67.
So for E squared Q smaller than 4 pi over square root of 3, there is definitely the stable fixed point. That definitely exists. But we don't know if this unstable fixed point survives. So this unstable fixed point itself begins to develop additional relevant operators. So what I'm saying is that there was this formula for the Wilsonite here. You might ask me, what about this? Do I need to include this? Well, it doesn't become relevant at the stable fixed point, but at the unstable fixed point, if we take the charge to be too low, it begins to be relevant. So we actually don't know the full phase diagram, even in a billion arbitrarily weakly coupled QED. That's why this problem is, I mean, it's far from the end. There is a stable fixed point, but what else, we don't know. This unstable fixed point here might be destabilized by quartics, and you have to renormalize them. So even in a billion QED, leave alone interacting gauge theories, there is no complete story for what is the space of Wilson lines which are conformal.
I think I'm missing something, Zohar. If I look at your formula for the dimension of mod phi squared,
Yes.
when Q is small, this is irrelevant.
Yeah, this is around the stable fixed point.
Oh, I see. There's another formula for the unstable.
The scaling dimension in the unstable fixed point is that it's 1. I think just let's go ahead after 2. So it's 1 minus the same square root.
What is the unstable fixed point from the bubble perspective?
This is this one.
Yeah, but is there you've written at the top there, phi equals 0? This is presumably the
Oh,
stable
it's
fixed point.
yeah, it's some kind of very subtle question about how fluctuations of phi decay as you go close to the nucleus. There are two choices. It's like two quantizations in ADS. You remember this special window where there are two quantizations? It's the same.
It's also there for Chern-Simons quantum mechanics.
Second.
It's there for Chern-Simons quantum mechanics. Just write down quantum mechanics for anions interacting. There are two boundary conditions.
Okay, yeah, it's probably the, I don't know that example, but it's probably the same. It's the decay of fluctuations near the Wilson line.
Isn't it kind of like just a 3D quantum mechanics problem? Maybe a relativistic one where we have this 1 over R potential and we have to regulate it somehow, and then
yes.
the unstable fixed point is when you're kind of on the verge of forming a bound state, whatever that is.
Well, there are bound states, we can talk about it, but there are these diving states. You remember the diving states? You know this word, diving state? It's not a bound state, but it's a diving state. It's much worse than a bound state. When you just have bound states, there is no problem. You don't reach the singularity. There's something called the diving states, which lead to a singularity. It's something worse than a bound state. Okay.
It's something that the Russians used to call the fall to the center singularity. It's kind of a little bit
worse than a bound state.
What's this limit when below which you potentially develop?
Yeah, so you get this formula from saying, okay, this is the scaling dimension in the unstable fixed point. If you take Q to be too small, this becomes very close to 0. Let's say if Q equals to 0, then this would be 0 because of the sign flip. So at that point, the unstable fixed point has tons of relevant operators that we didn't account for. So this lower boundary is derived from requiring that the unstable fixed point doesn't have relevant operators that we didn't account for, except for just this one. So I'm saying that when you start lowering Q, there are like directions that open up away from the blackboard that are also unstable, so we don't know what's going on there. Okay. Kind of done. I just want to make one comment about 2 plus 1D, and that's it.
Can I ask a quick question? Is the mass of the pile too big for this to be relevant actually?
Charge pile? Oh, sorry, what?
If phi is the pile?
If phi is the pile. Ah, you're asking how to
experimentally realize this.
Is the mass too big so that if I look at heavy nuclei?
Yeah, I think so. Yes, we try to see if it's actually easily observable in nuclear physics. Maybe they now have unstable nuclei with like 180. Well, in real life, fermions are better. I mean, you should really study QED with fermions. The story is almost the same. But you need nuclei of like charge 118 to see this phenomena. It's not so easy.
So there's E dagger E condensate?
Psi dagger psi, yes. Exactly. So the story that I told you here about bosons is almost verbatim the same for fermions, except that this is replaced by psi dagger psi. Almost the same. So the only major difference is that this becomes 16. So it changes the critical charge to 137, which is the inverse fine structure constant. But in graphene, the fine structure is lower, so it has a higher chance of being observable. Everything I said here about abelian QED is also true for n equals 4 superioung. There are no Wilson lines with large representations, and as you crank up the coupling, which is a free parameter in n equals 4, they disappear. So there are probably no Wilson lines at strong coupling in n equals 4 superioung, and that implies that there are no 't Hooft lines at weak coupling by S duality, and that's something we can actually verify. We verify that there is no 't Hooft lines at weak coupling, no conformal 't Hooft lines at weak coupling in n equals 4. Now I'll just make one comment about 2+1. We have many things to say about 2+1, but I ran out of time.
So one interesting example in 2+1 is 2+1 dimensional QED, which is f squared plus psi dagger, which flows to a fixed point, the bulk. This is the bulk fixed point, and you can add Wilson lines. So this would be like a charged impurity that you add to a 2+1 dimensional deconfined critical point.
So you can ask, you can try to repeat these computations here, and you can assume that there are NF Dirac fermions. So there is some line. Now it's a strongly coupled problem because QED in 2+1 is strongly coupled in the infrared, but Gabriel and Mark solved this problem for large NF.
Exactly. And they found that there are Wilson lines only up to an F over tau, which is a very cute result. It makes a lot of sense looking at the massive phases of this theory.
So in particular, for small values of an F, there should be one conformal charge impurity, or maybe two, but not more.
It should be observable, maybe. But yeah, this is just an example. You can do it in many other systems. And
it's kind of, at some point, it looks the same. All of them look the same.
Can one study Dirac fermions plus usual Coulomb? So that's a little bit like...
Yes, exactly, yeah. That's another thing we did. The situation of a Dirac cone in 2+1 coupled to a 4-dimensional Coulomb field is much easier than this. Because it's like this, but there are analogous results. There are again 2 fixed points, there is a flow between them, and it should be observable in graphene.
But because that's the graphene.
Yeah, that's exactly the graphene setup, and there should be such an energy flow in graphene. Yes. And also there, the number of charge impurities is highly limited. Maybe just 4 because of the coupling, and that's it.
But like some of these phenomena that you described, there was like some threshold charge. What are threshold charge in
graphene? It's probably 4 or 5. Yeah.
I think people even did some experiments.
Yeah. They already people tried to already put a large charge impurity in graphene, and they saw that it gets screened by some cloud of fermions, not of bosons, but still some cloud. This is I forgot the people who did the experiment, but this was already seen. However, they have not seen the 2 fixed points in the flow. This was not observed yet. They haven't seen the infinite order phase transition.